Thanks, Farhan. Hello, everyone. It's good to be back in person. And I'm Ankit Shah. I recently finished my doctorate at the Interactive Robotics group with Professor Shah. And this talk will be on interactive robot learning for non-Markov tasks. Initially, I'd like to start off with a demonstration of what our system can do, as that's a good place to ground what we did in terms of the technical contributions. So what you're about to see next is a person remotely commanding this robot to place objects on the table. And it's trying to teach the robot how to set a dinner table in a way that the user wants it to be set. So in the very first demonstration that was telecommanded, the robot places the dinner plate and the bowl. In the second one, you will see the robot place the dinner plate, followed by the fork, followed by the knife, and by the bowl. And now think about what the robot needs to do. So what you're going to see next is the robot asking 3 questions in terms of performing the task execution and then asking whether it is acceptable or not. So in the very first one, it switches the order of placing the bowl and the plate. And this is obviously unacceptable. So that's what the user tells the robot, that this execution is unacceptable. In the second query, the robot switches, places the fork, the dinner plate, the bowl in the correct order this time, but also places the small plate. And this is an unacceptable configuration. So now the robot knows that the small plate is prohibited. And in the last query, the robot does not place the knife, as you will see. Oh, I'm sorry, it does not place the bowl. And this is unacceptable too, because the bowl was a necessary object. So just based on this information, the robot now knows that the correct way of doing the task is placing the dinner plate and the bowl necessarily, and that the fork and knife are optional. So as you can see, in the 3 test rollouts, the robot has 3 different ways of performing the task. So this is possible because we are allowing the robot to reason about the uncertainty of what it needs to do. And we are also planning these policies by considering all possible options that the robot needs to perform. So here's our overall framework. In this framework, the user interacts with the robot through 2 modalities: by providing demonstrations or by providing acceptability assessments of the task executions performed by the robot. On the robot side, it is using iterative Bayesian inference to what the task specifications are, and it is doing this in an online manner, where after each task execution, the posterior of the previous iteration becomes the prior for the next one. Finally, the robot can refine its task specification in one of 2 ways. So one is it asks the user for new demonstrations, or in the second, it asks assessments whether the task execution it performed were correct or not. And the robot has the choice to decide whether the next iteration is going to be a demonstration or is it going to be a query where the robot performs and the user assesses. And finally, in deployment, the robot considers all the task specifications in its belief and then plans a policy that tries to maximize the satisfaction across all of them. I'll quickly go over this example where the robot is trying to learn or distinguish between these 2 specifications. So the first one says that do not place the fork. Second one is place the bowl, and don't place the bowl until the plate has been placed. And the second specification is don't place the fork and just place the bowl. So if the robot performs a task execution where either both are satisfied or both are dissatisfied, that's not very useful. So an intelligent robot will actually try to falsify one of them and then ask whether this is good or bad. And in this paper, we propose mechanisms to identify such informative states. Now, if you're looking at it from the teacher's perspective, the teacher knows what the true task specification is. So good teacher intelligently selects the next demonstration to maximize the robot's chance of learning the true reward function. And what we showed was that irrespective of the acquisition function for active learning or how good the teacher is, the robot can learn the true specifications given enough number of demonstrations as per the protocol. So that's it up. Thank you very much, and I'll be happy to take questions offline.
It works with Xiaolin for horizon integration, one context the enhancement of planning with estimated affordances.
Sorry, one sec. Good. Hello, my name is Aidan. I'm here to present our work on long horizon manipulation of unknown objects via task and motion planning with estimated affordances. This is joint work with Xiaolin, Fang, Leslie Kaebling, Tomas Lozano Perez, and Kaylin Reed Garrett. So in this work, we present a strategy for designing and building very general robot manipulation systems. Instead of the generality in design methods that is common in methods such as reinforcement learning or trajectory optimization, here we seek a systems generality. So what are the capabilities of a single policy without any additional task-specific reengineering or retraining? So essentially what we want to do is we want to place a robot in front of an arbitrary scene and have it be able to satisfy any arbitrary goal specified in first order logic. In this work, we present a strategy for doing just that. We call our strategy manipulation with zero models, or MOM. MOM is a closed loop policy that maps from RGBD images and robot joint encoder measurements to robot joint position commands. The policy is goal conditioned, and the goal is specified in the form of a first order logical expression that quantifies over object properties. At a high level, the MOM system uses task and motion planning, which selectively queries various perceptual modules such as shape completion, using modules such as shape completion, category agnostic, instance segmentation, and grasp prediction to find a plan which is feasible symbolically and geometrically. We show that this strategy leads to intelligent behaviors even without a priori knowledge regarding the set of objects, their exact geometry, and their affordances. So here's an example of the sort of test that we want our system to be able to solve. Here, the agent can only initially see, here it receives the goal of placing all objects in the blue region. It initially only sees the cracker box. And once it maneuvers the cracker box to the goal region, it sees two new objects. But unfortunately, it placed the cracker box at a bad pose, so it has to find a new joint positioning of the three objects on the goal region. And so it replans and packs all of the objects into the goal region. And after each step of replanning, after each step of execution, it's doing a replanning. So it's reperceiving and getting a new state of the world. And after it completes, it tests whether the final world state is satisfying the goal configuration. The core of our system is a task and motion planner, and we use Padiddle Stream as a framework to implement that. Padiddle Stream is a domain-independent framework for planning in mixed discrete continuous systems. During planning, the streams and samplers will be used to initiate queries when needed. And different queries may use different representations of entities, such as point clouds, meshes, or image properties, whichever is most appropriate for a particular query. And the key insight here is that you don't need to perform a reconstruction of the entire world state. You only need answers to a set of affordance queries that access the perceptual modules. So for example, if the goal is to pick up a banana, then you don't need to reconstruct or think about what the shape completion of is for a particular chair in the room. You don't even need the reconstruction of the shape of the banana. You only need a 6D grasp of the banana. So that's the only affordance query you need. Prior to this work, a common criticism of TAMP was that it requires known object models. And now using these learned modules and affordance queries, we're able to get around this constraint and still have the complex reasoning power inherent in task and motion planners. And then finally, here are some more video demonstrations of the MOM system. Here, the goal is to place all objects on opposite colored regions. And so you can see the complexity of the goals we're able to specify. It can also pick up any arbitrary shaped object, including non-convex ones. It can also pick up objects where the shape of the object changes over time. So here it did an improper segmentation, and then it's still able to achieve the goal with the broken parts of the toy. Here's an example where it's there's lots of objects obstructing the target object, and so it has to move those out of the way. And then we're also able to easily generalize it to novel robot configurations and camera setups. The only thing we change is the UREF, and it's still able to do all the same stuff. It's trying to move a green cup to a goal region, and it didn't see the green cup, so it hypothesized a possible location of the green cup, which was behind the largest object in the scene. And so it can also reason about uncertainty in identifying locations of objects that are specified in the goal. All right, thank you. Here's the links to the paper and more demos. Thank you.
It's too long.
Hello, my name is Xiang, and I'm presenting our work, Learning Task-Informed Instructions, a representation learning approach for model-based reinforcement learning in complex visual domains. This is joint work with Ge Yang, Pocket Agaro, and Tom Yakoda. Okay, so we've seen the model-based RL has achieved impressive results in continuous control and discrete control. And to make sure that the learned latent states fully encode information from the observation, a common approach using our model-based agents is to use the reconstruction laws to learn a pair of encoder-decoder networks. However, real-life control tasks are much more visually complex and often contains task-relevant information. To see this, let's first consider a simple experiment. We'll inject complex background noise or videos to the DeepMind control task cheetah run. We train the reconstruction-based streamer agent on these two domains. In the figure on the right, we visualize the policy performance in the vertical axis and vary the number of parameters in the world model along the horizontal axis by half, same and double of the original implementation. Not surprisingly, the performance with the simple background is only marginally affected by the model capacity, while the performance under the complex background, the agent's performance is much worse when you have a smaller model. So this trend indicates that the complex visual clutter stretches the modeling capacity of these model-based reinforcement learning agents, and thus makes it challenging to capture features relevant for solving the task. So the motivation of this work is to learn disentangled representation to resolve model-based RL in complex visual domains. First, let's take a look at how we learn the world model. Our proposal, learning task-informed instructions, explicitly models the task-relevant state and the task-irrelevant states in two separate streams, which we refer to as the task model and the destructor model, respectively. We incentivize the task model to capture task-relevant information by forcing it to predict the reward accurately. On the other hand, we discourage the destructor model from capturing task-relevant information by constraining it not to predict reward using adversarial laws. By having the two models jointly reconstruct the input observation, the task model can focus on capturing task-relevant information, but the destructor model is biased towards capturing destructing information. During policy learning, only the task model is used to generate imaginary laws. We simply imagine laws from the task model and train the policy through the active creative algorithm over the imaginary laws. Note that the destructor model is never used for model-based laws.
Okay, so here, let's look at some qualitative results. Now, on the first row, we show the raw observation from 3 different domains. In the first 2 domains, we have cheetah run, hopper hop. In these 2 domains, the yellow robot in the center are actually the task relevant object, whereas the video background is the distraction. Now, in the third column is this block world domain called many world. And we indicate the target location using the red sphere and try to control the blue block. The green and yellow blocks are distractors that move randomly. Now we can inspect the image reconstruction from Dreamer on the second row. Notice that Dreamer fails to capture the precise location of the agent because it does not distinguish between what is relevant to the task from like those background distractors. On the other hand, our method, task-informed abstractions, accurately captures the position of the agent. This is because distractions in the image are taken care of by this second distractor model, which enables the task model to focus on features that are relevant for the task. On the DMI control suite domain, we compare against streamer coloring red and strong model free baselines such as deep MDP in brown and the by simulation metric based baselines. Our method task informed abstractions outperforms all baselines in the cheetah run task. The black dashed line on the top are the arcal performance of Dreamer in the uncluttered clean environment. And the paper also provide evaluation on 10 DMC tasks in total. In these games, task informed abstraction consistently improves over Dreamer and outperforms all baselines in most tasks. We also present results on Atari games. Atari games naturally contains visual distractors, and our method improved over Dreamer's performance in several games. We compare it to Dreamer and strong model-free baselines such as DQN and Rainbow DQN. In Demon Attack and Yas Revenge, our method in blue outperforms these strong baselines for that are actually trained for 200 million steps, whereas our method is only trained for 100 million steps. In conclusion, task-informed abstraction enables model-based reinforcement learning in complex visual domains through a two-stream disentanglement scheme. Task-informed abstraction reduces to Dreamer when the distractor model captures no information and improves the performance when the irrelevant information are removed by the distractor model. The paper code and video can be found at the project website. Thank you.
Otherwise, we'll run out of time for the final speaker.
Yay. Okay, this time for real. So thank you for your patience, everybody. Really appreciate that. So I'm going to go super speedy because of this. So how do word representations geometrically organize linguistic abstractions? When we're talking about word representations, we're usually talking about the outputs of hidden layers in a language model like BERT. The idea is that these representations should encode linguistic abstractions about a word, like it's part of speech or its dependency relationship with other words in a sentence, because doing this might be useful for this task that it's trying to solve, namely language modeling, predicting a word given its context. In fact, we know from previous work on these representations that they do encode and post important linguistic features. We know this because we can train a model called a probe to reliably predict a linguistic feature given only the vector representation of a word as input. In the example here, the probe is predicting that the word joke in this sentence is acting as a noun. And it's able to do this only looking at the representations produced by the language model. So somehow this information does live within the representation. However, the accuracy of a probing model like this doesn't really tell us how the information is encoded in the model. It just tells us that it's there. What we're interested in this project is how linguistic features are geometrically encoded in the representations. And in particular, does this linguistic information live in a low-dimensional subspace of the representation space at large? So to answer this question, we're going to take the probing setting we saw before, where we train a model on top of the representations to predict these features, but we're going to augment it with a low-rank linear projection. And we're going to optimize both the projection and the probe in tandem. After we do that, we're going to sweep over projection ranks, training one probe per rank. And we're going to record the probe or the rank of the probe that achieves the same accuracy or close to the same accuracy as the probe trained on the full representation. So it'll look something like this. You start off with one rank, you keep going smaller and smaller until you're no longer close to the full rank accuracy. When you do this, what you find is that you only need 8 to 16 dimensions out of 768 for BERT, for example, to extract the linguistic information of interest, in particular part of speech and dependency relations. Both of these live in very low dimensional subspaces of their representations. These subspaces also have other interesting structure. You can find axis-aligned subspaces, for example, meaning that they correspond directly to components of the representation, but they're higher dimensional. And when the linguistic features exhibit hierarchical structure, so too do the subspaces. So inside the subspace encoding noun information, there's a smaller subspace encoding proper noun information, for example. And finally, we show in the paper that these low dimensional subspaces are causally related to the model's performance. So in particular, if you mask a word in the sentence and take the mask word representation and project it out of a subspace, encoding some linguistic information, you can make targeted changes to the model's behavior. Specifically, if you mask the subject of a sentence and project it out of the space distinguishing nouns, you can damage the model's ability to get the correct tense of the noun. So where it should be predicting a plural noun, it will now be much closer to predicting a singular noun. And you can see that by the points that are below the line here. That's how many it damaged the model's behavior for. So in conclusion, language models encode linguistic abstractions in this very geometrically compact way. These subspaces have a bunch of interesting structure and they are causally related to the model's performance. That's all. Thank you.
Oh, I see.
Do I need to?
No. So you're sharing something for it this way. You're not sharing full screen.
Yeah. I can also connect this. Right.
Hi everyone, my name is Tuan. I'm a postdoc in Josh Tenenbaum's group, and we're going to share a project that we have worked on together with people on this list. And so the starting point is that symbols are important for high-level reasoning, as we have seen in many talks today. Among other things, it's important for communication, planning, and abstract reasoning. And for concreteness, consider the scene where we see different objects, but we not only see where they are, but also how they're related to each other. So we can see there are two green pyramids, one smaller than the other. There is a yellow cube, and the smaller pyramid is on top of this yellow cube. And there's also this blue donut that is leaning on this big yellow cube. So the way we are going to model this is using a generative model that consists of discrete latent variables, here ZD, as well as continuous latent variables, ZC. So the discrete latent variables can describe like the high-level structure in the scene, for example, the scene graph, while the continuous latent variables can describe the exact locations. The X is the image, and there are also kind of learnable parameters of the generative model theta. So the goal of this work is to come up with an algorithm that can both learn the model, generative model, as well as a neural recognition model. So this is just a very high-level overview of the algorithm we propose, and in high level, there is a generative model, a recognition model, and we have this additional memory object which stores good elements for every observation so that we don't need to redo expensive inference again and again. And the way the algorithm works is that there is an objective to update each of these components. So this is unlike VAE objectives where there's like one objective that is unified and being optimized end to end. The advantage of this is that it can more easily deal with discrete latent variables. And just to illustrate this more concretely on an experiment with it, consider this image where it's where you can clearly see there are some primitive blocks. Here we probably some blue cubes and red cubes. And you can also see the structure that there are stacks, that there are 2 rows of stacks at the front, 2 rows of stacks at the back. And one thing that I would like to highlight here is that since we are embedding this in a generative model framework, we can handle uncertainties. For example, in the back left, it's unclear whether that stack has what is at the bottom of that left back stack. So we, using our algorithm, we also learn the primitives. So those are the generative model parameters, as well as the inference, which produces the following posterior. So one of the posterior samples says that, well, the back stack has this red cube at the bottom and then a blue cube on the top. There could be another explanation that at the bottom there is a green cube and on top there is a blue cube, or there could be a less likely explanation that the back stack is consists of red cube at the bottom and green cube on the top. We also tried another domain that is inferring compositional kernels on time series. And yeah, that's all. Oh.
Everything look good? Cool. All right. Hi, everyone. I'm Kevin. I'll be presenting our recent review paper entitled Advances in Inference and Representation for Simultaneous Localization of Mappings. This is not really your typical research talk, but I'll give kind of a high-level idea of some of the key points that we tried to emphasize in this paper. And then if you're interested, I have some links to the reference at the end. So when we talk about SLAM, broadly, we're usually interested in estimating a fixed frame for our robot consisting of an orientation and a position in 3D space, ideally in the same reference frame as our desired goal state. And optionally also, some environmental landmarks, let's say, to keep track of that state. And sometimes we're interested in only knowing the state of the robot right now, but in other instances, we're interested in knowing the entire history of states of the robot. And in particular, the kind of recent formalism of this problem that has become standard is to treat this problem as one of estimation over a graph. So we formulate this graph where the nodes are latent variables of interest, like the robot poses, or the landmark locations, and edges correspond to measurements between these latent variables. So let's say a measurement between two poses might be wheel odometry, a measurement between a pose and a landmark might be like a camera measurement of a feature in the environment or something like that. And this formulation has led to remarkable progress, right? This has led to widespread availability of open source SLAM solutions like OrbSLAM pictured here. Numerous benchmark data sets have led to really, really high quality visual and letter-based SLAM implementations, and even to the extent that we're able to have commercial applications of some of these technologies. So what's really challenging about robot perception? What's left to work on, right? In particular, we focused on three key topic areas. The first would be performance limitations and guarantees. So what are really the key quantities of interest that dictate the performance of an estimator for SLAM? Things like robustness and long-term autonomy. So how can we actually have SLAM systems that operate in the wild for extended periods of time without breaking when we get a single bad measurement, let's say. And then finally, developing richer large-scale representations, including leveraging semantics and being robust to things like dynamic environments. So on the inference side, we talked a little bit about performance guarantees for the SLAM methods that we're interested in. In particular, this is absolutely crucial for things like safety critical applications, right? And recent SLAM techniques have become available that are able to efficiently obtain verifiable solutions where we can actually guarantee that we've attained the global optimum when it comes to these sorts of estimation problems. And moreover, more recent methods have dealt with things like robust estimation where we're able to actually dynamically filter out outliers during the estimation process. And finally, we talk about things like information theoretic limits, things like Cramer-Rao bounds for the estimators, which historically have only been addressed in the linear case. We've now adapted more recently to nonlinear settings. On the representation side, we've talked about things like unifying semantics and geometry. So how can we actually couple semantic inference, like things like the measurements that we might get from an object detector with a global geometric representation of the world? And things like going beyond static worlds where maybe these objects are now allowed to move. How can we capture those types of features of the environment? And how can we represent them in a SLAM systems model? And finally, things like abstraction and hierarchy and representations are a key active area of research. And also things like learning centered and learned representations. So thinking about how SLAM might interact with the learning process. And so I'll wrap up there. But if you're interested in any of these topics, we talk about all of this stuff and a whole bunch more in the paper, which can be found here or at this link. Cool, thank you.
Hi, can you guys see my screen? Right, hi. I'm Ramin Hasani. I'm a postdoc at Daniela Russa's lab. Today, I'm going to present two papers of ours. So the first one is on causal navigation by continuous time neural networks. So last year, we developed a technology called neural circuit policies, where you can perform end-to-end navigation or end-to-end control of robots with a condensed network that is consists of differential equations. And this network was actually giving rise to some sort of attention map that was focusing on the true causation of the task under test. This was as opposed to like feed-forward networks where you have the attention of the network. For example, here, the lighted regions of a CNN network that is actually focusing on the outside of the environment. And then this kind of representation with a little bit of noise on top of the image would scatter the attention of the network and make the decisions of this network unreliable. So in a standard neural network architecture, you would have a kind of possible connections between two nodes of the system with activation would be like this. The networks that we introduced was liquid networks, basically, that each node is a differential equation, and the nonlinearity of the system is on the synapses of the system. And yeah, so when we have this nonlinearity, we actually gave rise to some sort of dynamics of sorts. So as we see here, if we compare the attention map of, like on this lane keeping task, if we look at the attention map of different types of neural networks, we see that our solution is actually the only one that consistently look into the road's horizon when taking a decision. So in the new paper, we actually asked why this is the case, and we formulated the mathematics of liquid neural networks together with the dynamic causal models, and we figured out that there is actual liquid time constant networks are nonlinear version of dynamic causal models. So dynamic causal models actually allow for intervention to the interaction of two basically differential equations of the system with like some linear parameters, whereas a neural network actually triggers the interaction of two different differential equations in liquid neural networks. And that was actually the root for that. And we tested this on a bunch of visual navigation tasks of, you know, like we trained them on passive data in simulation, in an imitation learning scenario. And we see that like when we look at the attention, we see that the task underlying task has been learned by the network properly. We check this, the closed loop performance of our type of network compared to the other models under different uncertainty variables. We see that the performance of these networks are significantly better than the others. So of limitations of these liquid-based neural networks is the complexity of the system that is dependent on the complexity of the ODE solvers that they're using. So basically you will, if you have a stiff problems and you have like larger scale models, then you have long-term long training and testing time for larger networks. So one solution is use the stable fixed step ODE solvers. You can also use hyper solvers, or you can find a closed form solution for neural networks. That's actually our next paper again. And in our recent work, we actually showed that you can have the same architecture that I showed for the end-to-end training. You can take that differential equation and actually find an approximate closed form solution for that. And that closed form solution is basically, I'm just showing one of the neurons in the representation of this network that I showed at the beginning, that you can actually compute the same, with the same accuracy, the same kind of patterns. And then we actually constructed, based on this closed form solution, and a new gating mechanism that time actually appears in an implicit fashion inside the equation. And this kind of system in sequential data modeling can actually outperform significantly advanced ODE and non-ODE recurrent neural network-based models. So if you want to play around with these liquid type of networks, these are the sources where you can look at. Thank you.
All right, so this is a question answering input with context and target answer and question, and we can do generation or extraction to get to predict the answer. Our goal is to learn high quality QA model on the unannotated
target domain. Since the annotation of QA model is, to learn QA model is very expensive, sometimes needs rich domain knowledge. So we have two scenarios. Firstly, we can handle the domains with no annotation at all, or we can have domains with annotated answer entities. For example, this CDC COVID guideline with highlighted important spans that are potentially answer entities. So what we do is we first collect a seed data set. For example, natural question or Scott, we have annotated context, answer, question triples, and then we train three models. Firstly, answer entity recognition, and then question generator, and then a pre-trained QA model. And then we adapt these three models to the target domain and generate training data on the target domain. So the pipeline looks like this. So we had first train three models and apply these models to the target domain. And we filter the generated QA data to select the high quality QA pairs. And then we fine tune our generation model on the selected data and rerun this pipeline to generate new training data. And after all, we train a new QA model on the generated data and then evaluate the model on the target, the test set of the target domain. Firstly, we talk about the AER model, which is answer entity recognition. We have a bunch of name entity recognizer out there, but we cannot use this because the answers are not always name entities. For example, this in this example, the answer is a reason, but it's not a name entity. So the AER output look like this. So given a passage, the potential answers are all annotated in color and underlines, and you can see that some answer entities are overlaps. And given an answer entity, we have a question generation model to generate a question, and we call the great. And we call the recognized answer entity answer ground truth. And after getting the generated question, we predict the answer with a pre-trained QA model. And the predicted answer is answer predicted. So they might be different from with each other. So since the generation models are not perfect, so we will need a method to filter the generated data. So we hope the generated question can lead the QA model to find the recognized answer entity, and we also hope the question has low perplexity, so that can be a high quality QA pair. So after getting the high quality QA pair, we reward our question generation model by fine tuning the model on the high quality generated data. So this is a pipeline, and then we evaluate on our target domains. So on Scott, we can see that the AER model with cooperative search, which is a search method we showed previously, had the highest performance comparing with other methods, and the NER performance pretty low. And after using our full model, we get pretty close results comparing with the baseline with a fully supervised model. And this is a performance on the MRQA benchmark. This is an example of a generated passage, and you can find more examples in the paper. And thank you very much.
Hi everyone, my name is Ziqi Lu. I am presenting today the consensus-informed optimization over mixtures for ambiguity-aware object SLAM. This is a joint work with Xiang Huang, Kevin Doherty, and Professor John Leonard. And the same paper is also going to appear in AROS 2021 next week. In this work, we developed a real-time robust object SLAM system that is aware of ambiguities in object pose measurements. We know that object-level maps have a great potential to support robot environment interactions, but individual object pose measurements usually are not enough to recover the full 60 pose of an object. For example, if the robot sees a coffee mug but cannot see its handle, there will be multiple possible interpretations for the robot pose and the mug pose. To resolve this, we used discrete multi-hypothesis post-representation to quantify the uncertainties in ambiguous object post-measurements. For the coffee mug, we can make multi-hypothesis post-estimation for it if its handle is occluded. Another example is a symmetric playing card. If we place a card on the ground, it will appear exactly the same to robots viewing it from opposite angles. So this will confuse the robot about its own pose. And to resolve this, we use two pose hypotheses to represent the pose of the card. And to handle all the multi-hypothesis pose estimations from the front end, we will need a backend algorithm that is able to tolerate all the pose hypotheses, track them forward in time, and later disambiguate them. In this work, we use the max mixture model to efficiently keep track of all the pose hypotheses, but unfortunately, its posterior is multimodal, so its solution is likely to be tracked in some local optimum. And in this work, we will use consensus over the pose hypothesis from the measurements to guide the optimization towards the global optimum. To evaluate our approach, we conducted two object SLAM experiments. The first one is using playing cards as landmarks, modeling the symmetric property of daily objects. We placed 40 playing cards on the ground and controlled the robot to follow a lawnmower pattern path, and each card is first observed from one angle and later reobserved from the opposite. And we can see our method is able to jointly handle the unknown data association and object pose ambiguity. It can continuously minimize these errors in the SLAM estimation, but the single hypothesis method failed catastrophically after the first card reobservation because it's not aware of the pose ambiguity. The second experiment is conducted in Unreal Engine. We placed 10 coffee mugs around some obstacles and control a simulated card to circle around them and collect data. We made a synthetic mug pose multi-hypothesis mug pose estimator, which is able to produce 3 hypotheses in a measurement when we are looking at the coffee mug from a handle occluded viewpoint. We used 4 different methods to process the data, and our method at the top middle is able to achieve more accurate SLAM estimation compared to other state-of-the-art algorithms. That's all for the presentation, and thank you for listening. Please check out our paper and video if you're interested. Thank you.
Hi, everyone. Can you hear me? That's a yes. Great. I'd like to start by providing a bit of context for Neural MMO, our open source research platform targeting the reinforcement learning and neuroevolution communities. When we think about large pre-trained models in vision and language, recently dubbed foundation models, the importance of data sets is generally understood and straightforward to explain. We need lots of images of different objects and places, or we need a large corpus from diverse sources that captured varied phrasing and idioms. But in reinforcement learning, this data dependency is harder to pin down. To attain broadly competent agents, do we need a lot of samples? Do we need more environments? What about the content of the environments themselves? How does that factor in? Neural MMO is a research platform for, to coin a phrase, foundation policies, analogous to foundation models, or rather, it's the start of it. The project was inspired by massively multiplayer online role-playing games, which place thousands of players in a persistent world with open-ended objectives. Having originated in the 90s, MMOs feature a number of design choices that maximize game complexity on a tight computational budget, which makes them much more feasible for agent-based research than intensive real-world physics simulations. Neural MMO leverages these techniques to efficiently simulate populations of learned and scripted agents in procedurally generated virtual worlds. Our baselines consider scales from 128 agents simulated for several minutes to 1,024 agents simulated for a couple of hours. And we are able to train on 19 years worth of simulated gameplay in just a few days on a 1 GPU server. Rather than a single fixed game, Neural MMO provides a set of modular game systems that users can individually toggle and configure. Think of this as somewhere between procedural level generation and an environment creation engine. Neural MMO provides deep customization options depending on your research goals without having to write environments from scratch. Our experiments range in complexity from basic resource collection to joint exploration, foraging, and combat in large environments inhabited by various scripted agents. The platform provides a standard environment interface and an active community Discord server for discussion and user support, as well as a visualization suite that allows you to overlay interpretable 2D heat maps, quantifying behaviors such as exploration inside of an interactive 3D client. We include tuned RLlib examples for policy evaluation against known skill scripted opponents in parallel with training, and logging integration with WenDB for experiment management, as well as an API for computing your own overlays in order to maximize interpretability for your particular application. Our best pre-trained baselines slightly surpass scripted baselines hand-coded with domain expertise on a few simple tasks, but really we're barely scratching the surface of what is possible in more complex configurations on larger environments. In addition to reading the paper, you can learn more about Neural MMO and join the Discord to connect with other users at neuralmmo.github.io. This is also the best place to contact me. Thank you very much.
Okay. Can you hear me? Oh, sorry. Okay, so to reiterate, so you have this pre-training objective, and usually your pre-training objective usually looks something like you take a sentence from a large text corpus and you mask out a particular set of tokens, and then you train the model to try and reconstruct the masked words. So the advantage of this type of self-supervised training is that you can scale it up with very little human effort. And indeed, current language models are pre-trained on huge amounts of data compared to human language learners. But on the other hand, they also have much weaker signal than humans. So as humans, we learn not just from words, but also from speaker intents and perceptual contexts. But are these additional extra linguistic signals really necessary to learn meaning? So even without grounding, language models seem at least some of the time to be able to generate coherent and plausible discourses. So this could suggest that these language models are simply just really good at modeling co-occurrence patterns between surface forms and text, or it could mean these models are actually do represent in some capacity the meaning described by text. So which is it? In order to answer this question, of course, we need to first be concrete about what we mean by meaning. And here what we do is we take the meaning of a discourse to be the state of the world that results from all events described in the discourse. So every time a sentence is uttered, we update the world state to account for the new sentence. For example, you see an open chest containing a key, you take the key, this updates the world state such that you now possess the key and the chest is now empty. And certain updates here, for example, the emptiness of the chest may not be explicitly stated in the text. Okay, so now that we have this formalism, how do we figure out whether our language models build these kinds of states? So what we do is we follow a paradigm called probing, where we train a language model, and then we freeze its weights, and then we train a low capacity probe to try and extract a particular linguistic property that we're interested in. So in prior work, people have used probing to extract things like parse trees or dependency relations. But what we do here is we want to extract semantic representations. And to do this, we're going to use a linear probe where the only free parameter here is this single weight matrix W. And we break down both the semantic state into its propositions, as well as the language model representations into contextualized tokens. And we take these pieces and try and classify the truth value of each proposition. Okay, so the important part here is everything except for the W matrix is frozen, meaning if we can succeed at this task, then these propositions are already linearly encoded by the language model. So how well do we do? Well, we evaluate 2 language models on 2 English language domains, and we find that for all of them, entity states are actually recovered to a fairly high degree of accuracy. And in particular, any amount of self-supervised language training outperforms a randomly initialized model, but also large-scale open domain pre-training is actually more beneficial than smaller scale domain-specific fine-tuning. We also investigate where exactly these entity states are localized, and we find that information about the final state of an entity is local to mentions of that entity. So we can read off the final state of the third beaker from initial mentions of that beaker. This means language models represent state in a structured and interpretable manner, meaning we can also manipulate their states in structured and interpretable ways. So we create these 2 language model representations A and B, and then we splice together the piece of A, which encodes the emptiness of the first beaker, with a piece of B, which encodes the emptiness of the second beaker. And we create this representation, which encodes that the first 2 beakers are empty, and generations from this will actually be consistent with this state. Okay, so in summary, we can learn the rudiments of semantic representation from just language. However, this is still far from perfect, and there's lots of open questions into what the limits of self-supervision are and what kinds of things grounding might help with. Thanks for listening.
Yeah, that's all for today. Thanks for coming, and hope to see you next week. Thank you.